So here is our main formula from last time to do spherical coordinates. We switch x, y, and z using these conversions going in there. We throw in the extra factor of rho squared sine phi. Let's go ahead and do some examples here. So let's integrate f of x, y, z is x squared plus y squared over the top hemisphere of radius 4 was centered at the origin. So an idea here is just going to be top hemisphere, not the bottom of the sphere, but just the top hemisphere. What are our bounds? We need bounds on theta and phi and rho. Okay, so we'll do it in the xy plane. We do one full loop around the circle. Theta runs 0 to 2 pi. For phi, that's the angle from the positive x-axis. So pointing straight up at our sphere, that's phi is 0. When the hemisphere hits the xy plane, that is phi is pi over 2, just like that. So phi runs from 0 pi over 2. If it was the entire sphere, this would be phi going to pi, but it's only the top hemisphere, so pi over 2. And rho runs from 0 to radius 4, so the biggest rho can be is 4. Okay, so our bounds here, theta running from 0 to 2 pi, phi running from 0 to pi over 2, rho running from 0 to 4. Okay, so the last thing we have to do here, x squared plus y squared, we need to convert that to spherical coordinates. So x squared plus y squared using our spherical coordinates conversion here, x squared is rho squared cosine squared theta sine squared phi. I just squared that. Now let me add to it squaring this. Plus rho squared sine squared theta sine squared phi. And note here, we can factor out rho squared times sine squared phi times cosine squared theta plus sine squared theta. Hey, that's just 1. So this is just rho squared sine squared phi. So rho squared sine squared phi goes up here. But then, don't forget, we always have to throw in, always have to throw in the extra factor of rho squared sine phi that we always just throw that in when we're doing spherical coordinates. We'll see why next section. D rho, d phi, d theta. Okay, so this is the integral that we need to evaluate. Take a look here. I think we can combine these together to rho to the 4th sine cubed phi. And once again, this integral is going to factor out as a product of 3 separate integrals. So theta runs from 0 to 2 pi of d theta. Everything here, like bounds don't, rho bounds don't depend on theta and phi. We can write this as the product of something that depends on rho times something that depends on phi here. Okay, the next one, phi runs from 0 to pi over 2 of sine cubed phi. d phi. And then rho runs from 0 to 4, rho to the 4th d rho. Okay, what is going on here? That is going to be 2 pi. And this over here, integrating rho to the 4th, We get rho to the 5th over 5, plug in 4 and 0. That's just going to give us a 4 to the 5th over 5. And then how to integrate sine cubed phi. This is an Calc 2 thing. Let's just remind ourselves how to do that. We would rewrite sine cubed phi as sine squared phi times sine phi, and then rewrite sine squared phi. So sine squared phi becomes 1 minus cosine squared phi, sine phi d phi. So this we rewrite sine cubed phi as sine squared phi times sine phi, rewrite sine squared phi as 1 minus cosine squared phi. Why do we do this? So that we can use substitution here. U is equal to cosine phi. Du is equal to negative sine phi d phi. Negative du is equal to sine phi d phi, so that's negative du. Okay, 2 pi times 4 to the 5th over 5 times, okay, what happens here? So 1 minus u squared, negative du. What are the bounds of our integral? When phi is 0, cosine of 0 is 1. And when phi is pi over 2, cosine of pi over 2 is 0. Okay, so what happens here? We get, let's see here. So there will be a minus sign there. Antiderivative 1 will be u, and that will be u cubed over 3. And plug in u from 1 to 0. And so this should give us 2 pi times 4 to the 5th over 5 times negative 1 times negative 1 plus 1/3. And that should simplify down nicely. So yeah, once again, we see here integrating over a spherical-like region, we should think about integrating using spherical coordinates.